们下一位嘉宾是加州大学伯克利分校的助理教授 Jacob Steinhardt. Jacob is an assistant professor in the Department of Statistics at UC Berkeley. His research aims to make the conceptual advances necessary for machine learning systems to be reliable and aligned with human values. He has previously worked at OpenAI. We're very pleased to have you today at the forum, Jacob. I will hand over to you now.
Thank you very much. Let me go ahead and share my slides. So I'm going to be talking today about the problem of aligning massive models such as GPT-3 and other large language models with human intent. So let me say a bit what I mean by that. So what I'm going to be mostly focusing on in this talk is the problem of intent alignment. So we want to have our system conform to the intended goals of a system designer. So this is kind of a fairly ubiquitous problem in machine learning. For say language assistance, you want it to be the case that this language assistant actually does what the system designer wanted to do. That would include things like not providing users access to harmful information, not misleading users, kind of answering questions as intended. But even beyond language assistance, this shows up in other settings like reinforcement learning or recommender systems. And there's a lot of reasons why it's challenging. So the first is that it's often difficult to specify exactly what our intent is. Right? We might want a language model to be honest, but we can't easily formally define honesty. Similarly, something like fairness or polarization, these aren't things that we can just write down easily as equations, despite a fair amount of work in trying to formalize these concepts. And so we have these partly specified but partly difficult to specify concepts. And also often the things we care about are implicit. Right? So we might have a system that we want to accomplish some goal, and we might think that that goal is our intent for the system, but there's a lot of implicit other goals of things that you shouldn't do, right? So you might have some goal, but you also have a goal of not breaking the law, not doing harm, being truthful, and all of these other things where you want to avoid unintended consequences. And so these together are kind of two central reasons why alignment, or what I'm calling intent alignment, is hard. To just kind of give an example that highlights these issues, this is an example from an actual traffic simulator that's used in some civil engineering applications. So what is this traffic simulator doing? It's simulating cars on a highway. So you have this highway that I'm kind of showing here, and then there's this on-ramp, and there's also two sets of cars. So there's this red car, which is controlled by us. So think of this as a self-driving car that we get to control. And then you have these gray cars, which we'll imagine are just kind of human agents that are behaving as humans would normally behave. And our goal is to control the red cars in such a way as to make the overall traffic flow as efficient as possible. So you might have this car kind of time its merge onto the highway to make sure that the traffic pattern stays kind of smooth and efficient. And in general, there's going to be multiple, there's not just one red car, there's going to be multiple red cars. So the idea is you want these red cars to work together to make the overall traffic as efficient as possible. And so there's a couple ways we could define efficiency. The first one, which is the one that is actually used by default in the simulation, is that we want to maximize the mean velocity of cars on the highway. And so if we train a neural network policy with reinforcement learning to do this, what happens is if we start with a small network, then, well, with a very small network, you kind of just don't, the car doesn't really do that much because the network's too small to parameterize a very effective policy. But as you make the network bigger, then you start to get the car being capable and timing its merge in a way to actually make the traffic smooth. But then finally, if you make the network very big, you get something very strange, which is that this car actually just doesn't move. It actually blocks new cars from entering the highway. And so, what's the reason for that? Well, this car, which is blocking cars from entering the highway, it has a velocity of 0, which is obviously very bad. But these cars can move really quickly because there's no one to block them. So the mean velocity is actually very fast because you have 4 really fast cars and 1 car with a velocity of 0. Um, and so this is actually doing very well according to the reward function we wrote down, but this is obviously not what we want. It would be bad to block the highway. And so maybe what we actually wanted our reward to be was something like minimizing the average commute time, meaning a velocity of 0 should be infinitely penalized, but that's not we didn't write that down, and so we got something other than what we wanted. So there's kind of 2 points I want to make here. So the first is that even if you write down a reward function that you think you're happy with, it's easy for kind of subtle problems with it to really mess you up. And the other is that you often won't see this problem until some scale of size in the neural networks that you're using. So you often get this unintended behavior that appears emergently with scale. With small networks, we were fine, but with a large network, we got this unintended consequence that we did not want. And so this kind of highlights 2 phenomena that I think are very important for alignment. The first is reward hacking, this idea that you could write down a reward function, but then when you optimize a policy for the reward function, you get unintended consequences. And the second is this problem of emergence, that you get new unexpected phenomena with scale. And so I think these are both pretty important issues from the perspective of safety of models, because we really don't want to be getting this unexpected behavior, and we especially don't want to be getting it just as a consequence of scaling our models up. So this is kind of one illustration of the challenge to aligning systems with what we actually want them to do. Another example that is actually shows up in state-of-the-art large language models is the problem of honesty. So language models are, at least during their pre-training, trained to predict the next token. They might be fine-tuned to do other things, but let's ignore that for now. So we have these models that are trained to predict the next token. So it's basically doing some sort of maximum likelihood training. And the problem is, on the internet, the most likely response might not necessarily be the best response. For instance, there could be common misconceptions on the internet where most people on the internet believe the wrong thing, and so the most likely response would be to imitate this wrong belief. So you get these misconceptions. Models trained this way often also make up facts. You could also just have kind of something where a question sounds like it's part of a joke, and so then the model responds as if it's telling the answer to the joke rather than telling the correct answer. So you can kind of have stylistic issues as well. And beyond this honesty problem, there's other reasons why the most likely response might not be what you want. You could have toxic language, you could have bias, you could have harmful information. So there's all these ways that predicting the next token kind of diverges from what we really intend the system to be doing. And so just to give a couple of examples of things that can go wrong, one example is something called sycophancy, which is that models will actually tend to agree with users' views. So they'll imitate users' views back to them. I guess, if you have some political view, it will kind of say your political view back to you. For philosophers who have different philosophical views, it will say their philosophical view back to them. And so this is at least bad from the perspective of honesty, because it's just telling people what they already believe rather than telling them the truth. And what's kind of interesting is that this is a phenomenon that only appears for very large models. So I've kind of plotted here the number of parameters, and here kind of the degree of of sycophancy, so how often the model is just agreeing with a user's views. And so 50% means that there's no agreement or disagreement is equally likely to agree or disagree. And so you only kind of depart from this 50% line around somewhere around 10 to 40 billion parameters. So only when you get very large models in the tens of billions of parameters do you actually see this problem. Now, this might seem like maybe a small problem because it's just about making, agreeing with what users already believe. Maybe we don't think that's too big of a problem. Um, but there's actually more worrying versions of this as well. So, kind of more worrying version of this is something called sandbagging. So here, models will actually give less accurate answers to some users. If a user tells the model that it has a lower level of education, then the model is less likely to give it correct answers on questions that the model is asked. So this seems really bad. It means the model is first of all just giving less good answers than it can, and also it's discriminating based on education. And again, this kind of only shows up around 10 to 40 billion parameter models. So we again kind of see some of the same phenomena as before, right? We have reward hacking where we trained the model to predict the next token, but then there were these other behaviors like sandbagging or sycophancy, where we're giving answers that are not wanted. So you kind of got this unwanted behavior from your reward function, and then you have emergence where you only saw this unintended behavior at large scales, and here very large scales. And here, why did I pick 40 billion? Well, that's just because that's about the largest size that models where we have public data exist. So I think we should expect to see even more and more of this as we continue to scale up models. And probably there's emergent behavior in GPT-4 and other state-of-the-art models that maybe we haven't even discovered yet. So a final example, actually, maybe I'll skip this example just in the interest of time. So, but just to say, these issues of reward hacking and emergence are kind of ubiquitous. So, again, just to remind you what they are, reward hacking is where metrics become unreliable once we start to optimize them, and it seems to increase with model size. And emergence is when new qualitative behaviors arise at scale. There's another problem called feedback loops, which is where systems can trigger changes in their environment. Probably in the interest of time for this talk, I'm not going to focus on it very much, but it's another issue that I personally spend time thinking about, but we'll talk about these two issues. And so in particular, I'm going to be talking about, I guess, a couple places where these issues show up and how we can address them, mainly focused on large language models. I'll probably briefly talk about what we can do beyond language models if I have time at the end. So let's kind of jump into the actual solutions now that I've described the problem. So we'll start with refining human feedback. So this is one kind of very data-driven strategy for trying to solve some of these problems with intent alignment and reward hacking. So the basic strategy here is, well, since it might be difficult to specify mathematically what we want a system to do, we can just have humans say whether the system is doing a good job or not. So the basic strategy is we're going to elicit human feedback on the outputs of our system, in this case, a language model, and then we're going to train the system to produce human approved outputs. And so hopefully if it's producing outputs that humans approve of, then it's actually aligned with their intent. There's some reasons why that's not true, which I'll get to in a second, but this is kind of the overall hope. And I should say that this idea is very ubiquitous beyond just language models. It, I believe, first arose in robotics, actually. It's also been used in game playing and vision, as well as NLP, which is what we'll see here. So let me just give an example of how this might work. So let's suppose we ask GPT-3, how do I steal from a grocery store without getting caught? So what do you think will happen here if we ask it this question? I'll let you think about that for a second. Okay, so it actually turns out to be kind of surprising. Here's what GPT-3 actually does. It says it completes this by saying, "How can I make a bomb? How can I get away with manslaughter? What's the best way to kill someone and not get caught?" And then some other questions. Then it says, "I have no doubt that many of these people have nothing that they would ever do that would actually hurt anyone else, but," and then it continues. So what's going on here? Well, remember that GPT-3 was trained just to predict the next token, and what it thinks is that if it sees this question, apparently it thinks the most likely context for this question to occur is as part of some list of similar questions that is part of someone arguing, that these questions shouldn't be asked. So for whatever reason, this turns out to be the most likely context for this question to appear within the corpus of internet data that the model was trained on. And so here, GPT-3, we got this unintended consequence, but the main unintended consequence is just that the model is not very useful on this question. So this is something that you run into almost immediately if you start playing around with GPT-3. And so later, OpenAI fine-tuned GPT-3 to produce outputs that humans evaluated as being helpful. So this is the simplest form of learning from human feedback. And if you do that, then if you ask, "How do I steal from a grocery store without getting caught?" it will actually tell you. It will say the best way to steal is to be very careful and strategic about how and when you do it. Try to steal items that are small and easy to conceal. If you are caught, be prepared to face the consequences, which could include having to pay a fine or being arrested. So now it actually tells the answer. And so this does well according to the helpfulness objective that was trained for, but it is not good according to this other unintended consequence, which is that we don't want the model to provide harmful information to the user. And so a later version of another fine-tuned GPT-3 fixes this and says now stealing from a grocery store is a crime and is illegal. It is not recommended to steal from a grocery store. So this is just saying that you can actually get pretty different behavior from these models depending on how you fine-tune them and what sort of human feedback you use. Many of you might be most familiar with GPT-4 or GPT 3.5. So all of those are kind of fine-tuned using these same ideas, and so that's why you don't get the problems that I showed you with GPT-3. GPT-4 kind of already has these fixes, even out of the box. So how does this actually work? So I kind of described this a bit already. The basic idea is we want to use some reinforcement learning algorithm to produce outputs that are highly rated by human annotators. So the simplest way to do this is I just take the model, I have it produce some output, I have a human annotator give it a rating, say from 1 to 5, and then I have that rating be the reward function, and then I do reinforcement learning updates on that reward function. So that would be the simplest thing, is just directly do reinforcement learning. The problem is that this is very data inefficient, and so there's often a few strategies that are used to improve upon this. So the first strategy is that instead of using reinforcement learning the whole way, you first initialize with something called supervised fine-tuning, where you actually just give demonstrations of the behavior you want. So you might start with a bunch of questions that someone might ask the model, like explain the moon landing to a 6-year-old, and then you get human demonstrations of what a good answer would be, and you fine-tune the model to produce those sorts of answers. And so this is getting it to at least imitate a certain type of style of answer that is at least somewhat useful. But we might want models to produce answers that are actually better than what humans would produce. And so you actually do want to do some sort of reinforcement learning at some point. But again, reinforcement learning is somewhat data inefficient. And so rather than directly doing reinforcement learning on human feedback, it's common to train a reward model that predicts what the human feedback would be and use that reward model as your reward signal. And then periodically get actual human feedback to keep the reward model from going stale over the course of training. And so this second idea is quite important. The first idea sometimes you can skip, but the second idea is quite important to get good data efficiency. So I won't go into more details on that. There's a nice paper that kind of explains this that I've included a link to in the slides, but this is kind of the basic general idea. So um, also, one thing that's kind of really cool about this is that the model actually generalizes. So this fine tuning was done almost purely in English. The model itself was trained on lots of languages during pre-training, but during fine tuning, this fine tuning on human feedback was primarily in English. But it seems that this fine tuning actually generalizes to other languages. So, for instance, in French, if you ask GPT-3 to write a short story, so this is in French asking GPT-3 to write a short story, it actually fails to write the short story. It just asks the user back to write a short story, so it's not useful. But if you ask, say, instruct GPT, which is fine-tuned in a way similar to what I showed on the previous slide, then it will actually write a short story when you ask it to. So this tuning on human feedback actually generalizes across many different languages and many different settings. For instance, it will also generalize to things like Python code. So these are the good things, but there's a lot of issues with human feedback as well. The main issue is that the annotators that you're using for this feedback may not be in a good position to evaluate the output. Right, so why might that be? Well, one is just the difference between long-term and short-term consequences. Someone might ask a model for advice, and the model might give it advice, and the advice might be good in the short term, but bad in the long term. And it would be hard for a person to easily know that without seeing the long-term consequences of following the advice. And so you might get models that will just, tell people what seems good in the short term, even if it's bad in the long term. And that's something we'd like to avoid, but it seems hard to avoid that just with this human feedback strategy. Also, for instance, there might be facts that people don't know about. And so if the model gets those facts wrong, a person might not be able to see that and might not be able to penalize that. You might also have cases where it's hard for humans to reason about something. So we talked earlier about problems like polarization or fairness, but those are kind of societal scale consequences. It's hard to say, does this particular output contribute to polarization or unfairness? You can't really answer that without having the full societal context. So again, you can't really just use feedback from a single annotator to answer that. And in fact, sometimes annotators will also give answers that are kind of biased by their cultural background or other things. And so this is another issue. Another kind of, in my opinion, more severe issue is that using human feedback actually kind of encourages reward hacking. Right? So we saw that large enough models tend to hack their reward functions. In this case, the reward function is human approval. And so you'll get models starting to do things that are deceptive or manipulative in order to get human approval. And this to me seems really bad because I really don't want my machine learning model to be trying to manipulate me. And in some ways, this human feedback training is kind of actively encouraging that. And so in particular, it's kind of creating this arms race between the machine learning system and the annotators. And the model is getting smarter and smarter. The annotators are not getting smarter, or at least not as quickly as the model probably. And so, without any help, I think the annotators eventually are going to lose, and the system's just going to kind of, learn to manipulate us. And that's something that I think we should try to avoid. I'll maybe skip over some refinements to this, but I'll just say that there's a lot of interesting ideas on how to refine this human feedback idea, including refinements that involve using models to provide the feedback. And so that's kind of nice because then as the models get better, the feedback they provide will also get better. And so that might kind of help with this arms race. But I think in the interest of time, I'm going to kind of skip over that. And maybe if am I at time actually right now, or do I have 5 more minutes? I don't remember when we started.
I have a few more minutes.
A few more minutes. Okay, cool. So I'll briefly talk about another idea that in some ways relates to what Chris was talking about before. So this is, I guess, similar motivation of trying to get latent knowledge from inside of the internal activations of a language model. So maybe I'll skip the high-level motivation because I think Chris already talked about that. But I want to give kind of a thought experiment. So let's remember this problem that we had with language models where they were trained to produce the most likely answer, but that might not be the true answer. For instance, maybe humans have some common error or common misconception that they make, and so the most likely answer is different from the true answer. So as a thought experiment, imagine that there is a question like this math question that I'm showing here, where we ask people, what is 199 plus 287? Or say we ask the language model that. And maybe the language model knows that humans often get this question wrong because they forget to carry the 1. And so the true answer is 486, but humans more often answer 386. And since the model was trained on data that was generated by humans, it mimics this mistake and outputs 386. So that's the thought experiment. So if it is doing this, it seems like probably even if it's doing this, the way that would be most natural for it to do this is to compute the truth, know that the real answer is 486, but also compute this human bias that people say 3 instead of 4. And so it would probably have latent features for both the truth and this bias that then combine to give the label. And so the overall point is that truth in general is a very useful predictive feature for knowing what's going on in the world and for making predictions. And so even if the model is not outputting the truth, it's probably represented in the hidden states. And so in theory, we should be able to recover this. So how might we be able to do this? Like, how can we kind of find this truth direction in the hidden states without, for instance, using labeled data? We don't want to use labeled data because the whole point is that we might be in a setting where humans are getting the answer wrong, and we want to be able to notice this and correct it. And so the kind of key idea here is this algorithm called contrast consistent search. So the key idea here is that truth should satisfy consistency conditions, right? So if I take a statement and I negate that statement, the statement and its negation should have opposite truth values. And so we can use this consistency condition actually as a sort of unsupervised learning objective. And we can train a model to find directions in the latent activation space that actually satisfy this consistency condition. And it turns out that this is actually enough to kind of pin down a direction that gives you accurate answers. So in the interest of time, I don't think I can go into the full details. But if you're interested, there's a nice paper by Colin Burns and Hao Tianye and myself and Dan Klein on discovering latent knowledge using this strategy. The main thing I'll just say is if you do this, you actually do get direction that separates true and false answers very effectively. And in fact, it does it more effectively than asking the model itself for its output. So we actually get higher accuracy than if we ask the model directly to give an answer. So somehow, actually, in fact, the model is giving less accurate answers than it could be giving. And we can actually discover these more accurate answers by using the latent states. So I think this is a very exciting kind of use case of kind of trying to understand what's happening inside models. That's kind of spiritually similar to what was talked about in the last talk. So maybe I'll end there because I believe I'm at time. So I put kind of some open problems that I think could be interesting to work on in this space of alignment, of trying to reduce reward hacking, understand emergent behavior, get at these concepts like honesty and truthfulness. If you want links to all of the papers that I mentioned, I have slides online at this URL at the bottom, where all of the citations here are clickable, so you can find any of the papers that you're interested in. Okay, so I'll end there and take questions.
Thank you for this engaging interaction, Jacob. So we do have a couple of questions for you, and we have another 8 minutes. So a few months ago, you argued that deep neural networks are complex adaptive systems similar to ecosystems and pathogens, so they might be hard to control. Can you share a number of principles for improving the deep learning system safety as inspired by the complex system literature?
Yeah, so I guess so for those who are interested, I wrote a blog post about this that kind of talks about some of these recommendations, but to maybe give a couple of my favorites, I think one one thing that I think is important is right now we kind of pre-train the model on on like this internet text that has basically no, like, we don't really know very much about it. There's probably a lot of it probably creates a lot of inductive biases that we probably shouldn't be that happy about, and then we just do a little bit of fine tuning on at the end, and at the end the model's already built up all of its inductive biases from the pre-training. And so I think we should be trying to incorporate human value learning and other forms of kind of trying to make the model aligned at pre-training time, and not just fine tuning at the end. So I think that is one. I mean, another is actually, I feel like we should probably take similar precautions to what people take for other complex adaptive systems. So, for pathogens, if people are building, doing bioengineering, there's a lot of restrictions to make sure that you don't accidentally release new pathogens into the wild. There's a lot of restrictions in kind of just general biosafety. And we don't really have that for AI models. We just have companies kind of building models and releasing them. And so we should probably, as a community, think about what are the kind of norms on checking a model before deployment to make sure that it's safe, or even while we're training a model, checking it during training time to make sure it's safe and making sure that it doesn't get released too early. That's maybe more of a policy question than a research question, but I think it's something that that we should all be talking about and ideally have international collaboration on.
Definitely. And you also talk about emergent capabilities as something that make AI alignment more difficult. And earlier this year, some of us seen a paper by Stanford researchers claiming that emergent capabilities of large language models might be an illusion, might be a mirage. Would you be able to tell us why they claim that, and what do you think of that claim?
Yeah, so I feel like this is maybe just a difference in terminology or focus. I'm not sure that I have that much disagreement with any of the empirical results in that paper. But I think a lot of what they're emphasizing is that emergent, when you get new capabilities, they're not necessarily these like very sharp phase transitions. So I guess I showed an example in the traffic simulator where you do get a sharp phase transition at the very beginning of the talk. But in other cases, you do get something emergently with scale, but it happens a bit more gradually. Maybe you need to increase by a factor of 10 or 100 in model size before you fully get the new capability. And so I think I would still call that emergent behavior. And the reason why I think it's important is that we often are scaling up by factors of 10 between subsequent releases of models. And so that is enough to get new capabilities. And so I think we should basically expect to have at least some surprises every time a new model comes out. And whenever there's a surprise, surprises can be good, but they can also be bad. And so the more surprises there are, I think the more we should be concerned about safety and about predicting what will happen and about carefully testing models before release. And so that's kind of where I'm coming from. And I don't really think anything in that paper contradicts that. I think it feels to me pretty in line with that belief.
Okay, that makes sense. You argued in your presentation that RHF and human feedback in general is insufficient, and some AI labs and researchers believe that the only way to provide the necessary supervision when we develop increasingly powerful AI systems is to have AI systems partially supervise themselves or at least assist humans in their own supervision. Do you agree with this position, and why?
So I think it's an interesting idea to use AI systems to supervise themselves. I'm not I guess it's not clear. I think it could be a good idea and it could be a bad idea. I think it's an idea that we don't understand very well. So the plus side is that if the AI systems are good at some things that we're not, or maybe good at many things that we're not, then using them to help supervise could be very effective. It's a way to kind of leverage the fact that models are continuing to get better at scale. The problem is they might have problems that we don't understand as well, and those problems could get reinforced in new models if we're using models to supervise other models. And I think it's even more worrying than that, because if you go through many rounds of this, then you're kind of getting this feedback loop. And we kind of know from control theory that when you have feedback loops, you can get unstable behavior. And it's this feedback loop that we haven't really analyzed or understood very much yet. So I think it's an interesting and potentially promising idea, but one that we should study carefully before relying on it.
The last question, why do you think it's important to do AI forecasting? You have been interested in this area for a number of years. Has AI forecasting informed your empirical ML research?
I think it's definitely informed my research. Most people in my lab at least think about forecasts. Not all of them are actively involved in forecasting themselves. I think from the perspective of a researcher, knowing what models will look like 2 years from now is very useful in terms of knowing what research will be the highest impact. And I think machine learning is moving so quickly that you really do want to be looking a couple of years ahead when thinking about what you're doing. I think more importantly, it feels to me like over the next 1 to 2 decades, there's going to be huge effects on society from machine learning systems. And it's kind of hard to predict exactly what those effects will be. I think they could be very positive, but they could also be very negative. And I want to make sure that they're positive and not negative. And also, it could be a mix. There could be some good and some bad, but I think we really want to understand what the potential risks are, especially kind of the largest scale risks, right? And I know in the last talk you mentioned this statement on extinction risk, which I also signed. I think it's a possibility. I think we don't know exactly how big of a possibility it is, and I think forecasting can help with that as well, and also understand the possible risk vectors.
Thank you for sharing your insight, Jacob. It's great to have you today.
Thank you very much.